So with digital data, we map the bit to one of the signal levels and transmit a discrete pulse. We saw schemes like Manchester encoding is more complex, and the different schemes have different characteristics in terms of error detection, the spectrum of the signal generated. Then we saw what happens if we want to send, or we need to send analog signals. We have bits, digital data, but we need to send an analog signal. Then the very basic form is to vary the sinusoid wave based on one of those three parameters: amplitude, frequency, or phase. So we went through and showed briefly we can have amplitude shift keying, frequency shift keying, and phase shift keying. Next, we want to look at what happens if we have analog data with either digital signals or analog signals. To illustrate these, and in fact to illustrate all four of them, let's consider an example. This diagram shows our audio system in this room. We have the speaker, or the person speaking, not the speaker, that's me. We have a microphone. The microphone's connected by a wire to the wireless transmitter. So here's the wireless transmitter. TX is usually an abbreviation for transmitter. Then that transmits to the wireless receiver, which is here on the desk. And that wireless receiver is connected down to the amplifier in the cabinet here. So here's our amplifier. And that amplifier is connected via cables up to where are our speakers up in the ceiling in this room. So connected to multiple speakers. And you are the listeners here. So that's one case. We'll consider the rest when I go through the laptop a little bit later. First, what case do we have? Start with the data, analog data. The voice I'm generating is analog data. What about into the microphone, or the microphone to here? It's in fact analog. So there's no easy way to know. So what happens is that as I talk, the acoustic waves, the acoustic signal hits the microphone, which converts that into an electrical signal. And it maintains the same frequency, same characteristics, and sends that across the wire to the wireless transmitter. So what we're dealing with is we have analog data, and that's being transmitted as an analog signal from the microphone to the wireless transmitter. The wireless transmitter here also transmits an analog signal to the receiver, so we also have analog here, except it transmits it at a different frequency and with a different spectrum. That is, the input data is my voice. The microphone takes that as is and sends a signal. So the first analog signal going from microphone to here looks the same as the input analog data. I'll show you a picture or a diagram that shows them in a moment. Then this wireless transmitter transmits that information to the receiver, but it actually shifts the frequency in which it transmits. My voice is ranging from 0 hertz up to, say, 4,000 hertz, plus there may be other noise around. But the transmission from here to the wireless receiver is at around 600 megahertz, or close to 700 megahertz. But still using an analog signal, the wireless receiver receives the analog signal, shifts it back to the original frequency of my voice, sends it to the amplifier. The amplifier increases the amplitude of our signal, sends it to the speakers, and the speakers take the input electrical signal, representing my voice, and simply converts it to an acoustic signal, sound waves. And they're sent down to your ears and you receive that analog data. So that's the process where we have analog data, and in fact all the way we're using analog signals. we'll look at another case where we use digital signals at the moment. What's the analog data look like? This is a diagram showing the analog data, or a portion of analog data, voice, over time. So the blue plot there, we see time and the intensity, the signal strength of that data. So this is just a recording of the voice from the lecture yesterday or the day before. So over a period of 5 minutes, all it's showing is the plot of the of the data as a function of time. And in fact, if this is the original analog data generated by me in this instance, then in fact the signal being sent to the wireless transmitter is in fact the same as this. There's no difference between the analog data and analog signal in that case. When we transmit it from the wireless transmitter to the receiver on the desk, that's the input, but in fact we'll see shortly that it shifts the frequency in the spectrum. It changes the signal to transmit wirelessly. So this is a plot of our analog data as a function of time. When we went through one of our first topics on data transmission, we gave a plot of the signal strength as a function of time in the time domain. And you have moments of silence, and when the signal strength goes up and down, and you can zoom in and so on there. Of course, we can look at this in the frequency domain as well, where each signal, so this is analog data and the analog signal sent, because it's the original data generated. Okay, just wait a bit, let other people listen for a moment. The analog data that is generated in this case is sent as is, as a signal. So the acoustic signal coming in that I generate is sent as an electrical signal in the same form as this. There's nothing is modified to convert from the analog data to the analog signal in this case. So in fact we can think this is the analog signal being sent here. It's also the analog data being generated. It's both. Any signal we know contains multiple frequency components. And we can plot a signal in the frequency domain. The peak signal strength as a function of the frequency, where we had plots of the impulses. But in practice, it contains many impulses. And a plot of this signal in the frequency domain is given by the software. So here's the frequency, and here's the signal strength. Signal, peak signal, that's an uppercase S, this is a lowercase s. This is a function of F, frequency. That's this one. We see the frequencies ranging from 0 up to, in this case, 20 kilohertz. And we see the signal strength. In this case, or in this software, the signal strength is reported in decibels. The most important thing to recognize here is that because it's decibels, that's a logarithmic scale. 3 decibels, a shift of 3 decibels is about doubling of the absolute value. What does that mean? It means at the top, the strongest signal strength is here at a frequency of about 500 hertz. And that's at around minus 48 dB. At minus 51, the signal strength is twice as weak as at minus 48. That is, at this line, or the line below, is twice as weak as the point at this point. That's just because we've got a logarithmic scale using decibels here. In other words, this point here, this peak here, which is around minus 60 dB, is, what have we got, 12 decibels different, so that's 16 times, this signal, or this component, is 16 times weaker than at this point. So don't be confused, because this is a logarithmic scale, even though it looks like the signal strength is strong here, it's in fact very, very weak compared to at this point. Most of the energy of this signal is concentrated in the frequency from 0 up to 3,000 hertz, with an exception up here. Because it's a logarithmic scale, in fact here, what have we got? Minus 66 dB is about 60 times weaker than here. And this is, of course, hundreds of times weaker than up here. So it's very strong, or it's strongest up here, it's strong here, it's actually quite weak in these frequency components. That makes sense to us because this is a plot of the frequency domain of voice, as a recording of voice. Most of the signal strength is in the range up to 3,000 hertz, because we know voice has a spectrum of about 0 or several hertz up, or several hundred hertz, up to 3,000, possibly 4,000 hertz. That's the most of the frequencies of voice. The rest is noise, really. Maybe objects moving, it may have been the air conditioner being recorded. There may have been some peak here from either an error or a problem in the recording, or maybe someone shut the door or something. That's a peak up here. So this signal that we're transmitting, most of the energy is in what we expect up to 3,000 hertz, 3 kilohertz. So that's our signal being sent to the wireless transmitter. What we want to do, so then we send it to the wireless receiver, to the amp and the speaker, and to your ears, and you receive the analog data. Another thing that we do is, of course, I record the voice on my laptop. So the other path is the amplifier is connected via a cable to my laptop, and it comes in, and my laptop takes the input analog signal, which is effectively this, takes that, and it converts it to digital. It converts that input analog to digital data, saves it as bits, as a file on my laptop. So that conversion from analog to digital at my laptop, we need to go through how that works. Of course, I save the file on my laptop. We'll look at the file, or a file that represents this, after we go through the conversion. The next thing I could do is send that file to another computer, to my computer in my office, or to someone else's computer, and I could actually stream that file so that someone sitting at another computer could receive it and play it on their speakers and hear that audio. If this is an Ethernet wired LAN link, I connect my laptop via a cable going up through the wired LAN in SIT to the destination computer. In fact, Ethernet uses digital signaling. It in fact uses Manchester encoding. We saw Manchester yesterday. So it takes the digital data generated by my laptop, the bits, where the bits represent, or the bits were created from the analog to digital conversion of the audio coming in, sends them as a digital signal to the receiving PC. It actually goes via other devices, but let's keep it simple. The receiving PC converts so it receives digital data, bits, it converts them back to analog and sends an analog signal to the speakers, sends an analog signal to the speakers at this computer, and that plays them to the person listening. So here's an example of using our digital data sent as a digital signal. If we go back to our slides, Manchester encoding is one of the examples we went through yesterday. Digital data as a digital signal sent across the wide LAN. Alternatively, I may not want to plug into the Ethernet and send wirelessly. So I can send from my laptop to one of the wireless access points outside. And in that case, we send an analog signal. So my laptop has digital data, the recording of the voice, and transmits an analog signal. So in that case, we need to use some shift keying technique to take that digital data and convert it to an analog signal. And so we covered the approaches yesterday of how to do either amplitude, frequency, or phase shift keying. In fact, wireless LAN uses a combination, I think, of amplitude shift keying and phase shift keying. So take digital data, send as an analog signal using a combination of amplitude and phase shift keying. Access point receives that, gets the original digital data back, sends it via, in this case, maybe via Ethernet again, as a digital signal to the PC, converts it back digital to analog, sends to the speaker, and the person hears that voice. So in this scenario, we've got all four cases. From the start, we're sending analog data as analog signals, and all the way through the speakers to you. If we go via my laptop converts the analog into digital. And if we go via the wired LAN, that's digital data over a digital signal. Over the wireless LAN is digital data over an analog signal. So we see a combination of all those techniques that we've gone through yesterday and today. What we need to do now is how do we convert from analog to digital? Because that's what we do when we want to send analog data as digital signals. We take the analog data, convert it to digital data, and then use one of our existing techniques to send digital data. The two previous techniques were digital data as digital signals or digital data as analog signals. So once we have digital data, we can use one of those techniques to transmit. So the main thing is how do we convert the analog to digital? And we use a codec. We encode the analog data at the transmitter and decode it at the receiver. Combined, those two processes are called a codec. There are different ways to do the encoding and decoding. Two common ways, or maybe the most basic way, is called pulse code modulation, and we'll go through that today. There's another one given in these slides, delta modulation. You can look at that in your own time, and there are others as well. These just show the basic principles. So let's go through pulse code modulation. Input analog data, such as my voice. The output wants to be bits, digital data. How does that work? What we do is we have an input analog signal, and we divide, if we look at the minimum and maximum magnitude of that signal, we divide it into different levels. We normalize that signal to a number of different levels, and then at a certain period in time, we take a sample of the input analog and match it to one of the levels that we've divided the magnitude into, and convert that sampled value into a code number, which is represented by an n-bit binary number. These are the steps best explained by an example. Here's our input analog data, this solid line here, representing just some small portion of, say, voice or any analog data. Continuously varying over time, continuously varying magnitude. First thing we do is we divide, so the magnitude varies from possibly down here up to here, so we divide this space into different levels. In this example, we divide it into 16 different levels. Over here, the normalized magnitude from 0, well, this is one level here, 2, and there's 16 possible levels here. We don't have to have 16, usually it's a power of 2, so it can be larger than 16 or smaller. We'll see the impact later. And this is time, so we can think we start here at time 0, we take a sample of the signal or the input as we measure the value. We measure the value on our scale and it comes to 1.1 at this point. And we map that to the nearest level. So anything in this range will map to level 0. We count the levels starting at 0. Level 0, level 1, 2, and so on. So up to 15. So 1.1 falls within the range of level 1. We could say that anything from 0 with a value of 0 to 1 is in level 0. We measure at this point in time the actual input analog data. Yeah, at this point in time. So if it's about 1.1 here. No, we haven't got there yet. We'll do that in a moment. Measure, so we're going to do it over time. We're going to take multiple measurements. At the first measurement, we measure here, it's 1.1. And we have 16 different levels. Anything between 0 and 1 we'll say is level 0. Anything between 1 and 2 is level 1, and so on. So we have input of 1.1, and therefore that's level 1, or the code number 1 is given to it. And we map that code number or level into a binary value. Because we have 16 levels, or 16 possible code numbers, we need 4 bits to represent any of those 16 values. With 4 bits, we can represent the values from 0 up to 15. That is 16 different values. So at this time point, measure 1.1, it corresponds to code number 1, or level 1, whichever way you want to think about it. And this is the decimal value. Convert it to a binary value, and we get the 4-bit number 0001. That's our first piece of digital data. Remember, analog data, we want to convert it to binary, to digital data. Then what we do is we repeat the process, but some time later. We take another sample at this point in time. We record the value. It's 9.2 at here, corresponds to code number 9, corresponds to the binary value 1001. And we keep doing that. We keep taking samples of the input analog data over time. As long as the input analog data continues, we'll keep taking samples. And at a regular with a regular sample period, TS, the time between samples. And in this case, we take the samples and the output, so the digital data representation of our input analog is this sequence of bits. And that's our final result. We've converted our continuous analog data into discrete values, zeros and ones in this case.
This is the bit seed for divide for one side. 4 bits for another quantized.
yeah, 4 bits for each sample in this case, in this example. If this was an audio file, then the data that I save on my laptop is really a sequence of bits, such as this. It represents the audio file. So the 2 parameters that we've got involved with this scheme is how many levels do we have. In this example we had 16. That is, we mapped to one of the possible 16 code numbers. And how often do we sample? What's the sampling period, or what's the sampling rate? We'll look at what's the impact of these 2 parameters shortly. So this is our digital data representation of our input analog data. At some stage we normally want to convert back to analog data. So if these bits are the file that my computer saves, my computer sends that to another computer, and that computer converts the digital data back to analog. So it takes the input bits and produces an output analog signal. Let's see how it does that. Let's try and draw what the receiver would do. What have we got? So input analog data, convert to the digital data, send those bits from the transmitter to the receiver. The receiver receives those bits and wants to recreate or reproduce the analog. So the first set of bits it receives, the first set of bits generated was 0001. If we sent them immediately, then the receiver receives those first 4 bits, 0001. That's the digital data it has. He wants to recreate the analog data, converts that back to the decimal value or the code number, 1, and now produces an analog output corresponding to that code number. So produce some output to the speaker, some electrical signal, maintained for the duration of the sample period. Actually, I'll use a different colour to make it a bit clearer. So our input digital data was 0001, or the decimal value of 1, corresponds to code number 1. So we produce an output for the sample period. This is the sample period here, at that level. The next value, so the next sample period receives the value 1001, which has the decimal value 9. So we produce an output at that level. Actually, let's try to map it to this diagram. 0. Oh, that's right. 9. And we'll continue to do that for each of the samples. The next one, 15. And then 10, 5, 2 and 2. I'm just writing the decimal values, but in fact we receive the binary value. We receive the bits. 10, 5, 2 and 2. That's our output analog data. At the transmitter, our input analog data was this continuous value. We convert it to digital data. We send that digital data to the receiver, and that receiver converts it back to analog data. But the receiver only has these bits. That's all it knows. Again. This is just so the code number is really indicating the level. If we divide the space into 16 levels, we take a measurement and we choose a code number which is the closest level. Map it to bits, send those bits. When we receive those bits, we do the opposite and produce an analog output at that level represented by the bits. 1, 9, 15, 10, 5, 2, 2. Is it the same? This is just showing the concept that, okay, if we start from 0 and go up to 16, then we can divide that into 16 levels, and each level is going to be represented by a code number. So one way to look at this diagram, any value measured in this space gets the number 0. Anything measured in this space between 1 and 2 gets the number 1. What is it? It's
the ceiling.
Yeah,
The floor.
it's the floor.
Floor.
So 0.9 goes to 0. 1.1 goes to 1. 15.9 goes to 15. We assume that there's nothing above or 16 or above. If the value is 1.9, if it's 2.1, it will go to 2. It's the floor. Mathematically, it's the floor of the measured value. Go down. Is the received analog data the same as the transmitted analog data? It's not the same. Does it look the same? No. Does it look similar? The shape is similar. It starts low, it goes up to a peak, it comes down. Roughly. So what we care about is how close is the received data to what was transmitted. How accurately do we reproduce it? Because we've got some error introduced here. In this case, of course, it doesn't look the same, but we can see the general shape. How can we improve the received data? How can we make it look closer to what was transmitted? Sample more often. What else? More levels, more code numbers. if we sample, let's consider sampling more often. If we sampled at this point, in the middle here, 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 and so on, that is, we have twice as many samples, can we quickly draw what we would get? The first value will be 1. If we sample here as well, we get somewhere which gives us a code number of 3. Be clear, we sample in the middle here. I measure that value as 3.7, which maps to the code number 3. So we would transmit and receive the value 3. So we'd produce an output at that level. And the next one would be 9. And then, because it's the same as this sample, then we have another sample here, which is what? 14 perhaps. And then 15. And then another sample here, which is maybe 14 again. Have to be more accurate. And then in the middle here, a sample of 7. So all I'm doing is introducing extra samples. Of course, the samples we've already got are the same, but we also have samples in the middle. After 5, measure here, let's say to be approximate, it gives us the value 4. Maybe it's 4.1 as a sample. So it gives us the value 4. 2. Here also 2, and the last one may be 3. So the red line here is the output at the receiver of the analog data if we double the sampling rate or halve the sample interval. More samples, you can almost see, but if you look at the red one, it's more similar to what was transmitted, our original data. Increasing the sampling rate increases the output, increases the accuracy at the output. When we reproduce the analog data, it's more accurate at the receiver. Have even more sample rates, more samples, an infinite number of samples, and we'll get perfect reproduction. So the smaller the sample period, the more accurate the reproduction will be. Similar concept, the more levels. What happens if we reduce the number of levels from 16 to 2? Here we have 16 levels. If we reduced it just to 2 levels, reverting back to our original sampling interval, the first sample would be what? So we have 2 levels, just 0 or 1. This sample would be 0, this one. It's above halfway, so it would be 1. It would be 0, 1, 1, 1, 0, 0, 0. So if I had to plot that, 0, actually we may draw it in the middle. So this is halfway. Zero, 1, 1, 1, 0, 0, 0. If you can see that black line, that would be output if we've got the same sampling rate, but we just have 2 levels instead of 16. That, of course, reduces the accuracy at the receiver. So increasing the sampling rate, increasing the number of levels, increases the accuracy of the reproduction at the receiver when we reproduce the analog data. What's the problem? File is bigger. So the advantage of increasing the sampling rate and number of levels is that the accuracy is better. The disadvantage is that the amount of data we need to store that analog is larger. Let's calculate as an example. Let's say our sampling period in the first case, TS, was 1 millisecond. 0, 1 millisecond, 2 milliseconds, 3 milliseconds. If I wanted to send this, just this portion of data to a receiver, and I wanted to send it such that we always receive a sample of bits every 1 millisecond, how fast do I need to send? How many milliseconds in 1 second? 1,000. Sampling period of 1 millisecond means 1,000 samples per second. So over a period of 1 second, I'd have 1,000 samples. In the first case, each sample was 4 bits. We had 4 bits per sample. Therefore, if we want to transmit this and receive it at the same rate at which we're sampled, then we'd need to send 4,000 bits per second. So I'd need to send at a speed of 4,000 bits per second such that the receiver always receives 4 bits every 1 millisecond and can reproduce correctly. If we double the sampling period, that was the red line. If we double the sampling period, sampling rate, so sample period is ½ a millisecond, sample rate is 2,000 samples per second. Increase the sampling rate, the accuracy will be better at the receiver, but we still have 4 bits per sample. We have 2,000 samples per second. We need to send 8,000 bits per second. That is, we need to send the data faster to get the accurate reproduction. Or we need to have more bits saved in a file. Because if I saved one second of audio in a file, in the first case I would need to store that file in 4,000 bits. In the second case I would need to store 8,000 bits on my hard disk. That is, I need a larger file if I'm saving it. For more accurate reproduction, we need larger space, or we need to send faster. That's the disadvantage. The same applies for code numbers. Here we had 16 levels, 4 bits. If I had 32 levels, I would have 5 bits per sample. These values would go up, but the accuracy would be better. Increase the levels, accuracy goes up, the amount of data required goes up. That's the trade-off. We'd like to have as small a file as possible, or send as little, or you send as little as possible per second. So that's pulse code modulation. That's the very basic way that we can encode analog data into digital data, and is used in audio especially for reasonable quality audio. So going back to our example of my audio, where is it? MP3 is slightly different because it also compresses. But yes, we'll see where bitrate comes in. Let's look at this example without compression. Yeah, a CD doesn't compress. So here's my audio. In this audio, I recorded the audio and the software had a sampling rate. You can see it up the top was slightly 44,100 hertz. Hertz is 44,100 samples per second.
This is for CD.
Yeah, this is what my software recorded, and it's the same format used for a CD. 44 kilohertz or 44.1 kilohertz. My software recorded samples with each number is represented by a 32-bit value. But when I save this to a file, if I save it to a wave file, you know, if I save this to say voice example.wav, I can choose the number of levels to save as. Yep. Hertz.
What is the length of one sample?
1 divided by 44,100. I don't know the answer. Yeah. So the inverse of that. So 44,100 samples per second. Yeah, the period is the inverse of this. This is the frequency at which we sample. The inverse of the frequency is the period of each sample. Save it as a file. In this software, when I save as a file, I can select the number of levels to save as. And I've done it before, and I chose 16-bit. That is, each level is represented by a 16-bit number. So in fact, we have 2 to the power of 16 code numbers or levels. In our example on the board, we had 16 levels. In this real example, we have 2 to the power of 16 levels, 16 million levels. How big is the file when I save it? How big is the file? How many megabytes is the file when I save it to my hard drive? Well, you have the information here. The duration of the file is up there. 5 minutes.
5 minutes.
A little bit more than 5 minutes. 5 minutes is 300 seconds. In fact, it's 310 or so, 307 seconds. So, quite simple, we have every sample is 16 bits. So the total number of bits that we have, 16 bits per sample. Every second, 44,100 samples in 1 second, 300 seconds. That's in bits. Convert it to bytes, it's around 27 megabytes. If you convert it to bytes. I've saved the file, and the actual size is up there, 27,090,386 bytes. So 27 megabytes is the actual size of the file. It was actually 307 or 308 seconds. So I think if it's 300, it's around 26 megabytes, so it's close. If we increase the sampling rate, if we double the sampling rate, we would double the size. If we decrease the number of levels, we would decrease the size. We'd like to have as small size as possible to represent this analog data. But the more bits we have to represent it, the more accurate the reproduction will be at the receiver. This is uncompressed. When you talk about MP3, MP3 actually does compression of the file. So we get much smaller file size with the aim of getting the same reproduction at the receiver. But compression's another factor. This is similar to what CD quality is. A CD uses a sampling rate of 44 kilohertz. I think it uses 16-bit, but it's stereo in a CD. There are two channels. In this case, it was mono. There was just one channel, so it would be double this. Or we actually have two copies of the audio, or two different audio streams. So 16 bits, but two different streams, so in fact, you need to double it. Two at a time. No, you just have two different streams. Yeah.
Left and right channel.
Yep.
Each one is 16 bit.
Yep. In this case, there's mono. If I had stereo here, when I record, you'd see another track here underneath it, just different samples.
How much does MP3 compress the file? Like how much percentage from the original file?
This is how long? 5 minutes? I think MP3 would get this down to maybe 5 megabytes approximately. It depends on different factors. That's a factor of 5. Sorry?
We cannot really recognize the difference whether we have that much.
Yeah, it depends how good. It depends on different factors of what the compression algorithm is. Because when you compress something, an MP3 is lossy compression. It takes those bits. So MP3, we originally have these 27 megabytes. If we compress that, in fact, we lose some of those bits. The way the compression algorithm works is to make it smaller, it looks for different patterns and uses a smaller number of bits to represent those patterns in the stream here. And when we decompress, we don't get all of the original bits back. Therefore, the quality is not going to be the same as uncompressed. But whether your ears can determine whether it's the same is another factor. In theory, it's lower quality, but in practice, it's hard to determine what the quality is. How often should you sample? So Nyquist did some work. The ideal sampling rate depends upon the frequency components contained in the signal. The analog data contains different frequency components. We saw in my example plot we had actually up to 22 kilohertz, but most of the energy was up to 3 or 4 kilohertz. The sampling theorem tells us that if we have some signal which has multiple frequency components, if we sample it at a rate 2 times the maximum frequency component, so a signal has a spectrum ranging from 0 up to 4,000 hertz, the maximum frequency component is 4,000 hertz. If we sample it twice that, at 8,000 hertz, then in theory we can reproduce the original signal in a perfect manner. That's what the sampling theorem tells us. Regarding the sampling rate, if you sample twice the maximum frequency component, you can reproduce all of the data. That assumes if you have an infinite number of levels where you can reproduce. But in fact, in practice, we do not have an infinite number of levels. We have a finite number. So for voice, for example, most of the voice is contained between 0 and 4,000 hertz. The maximum frequency component, 4,000 hertz. If we sample at 8,000 hertz, we should be able to accurately reproduce that voice. But how many levels do we have? Well, ideally we'd have an infinite number of levels, but we cannot do that. In practice for voice, 128-bit levels is generally considered good enough. That is 7-bit encoding, not 16 bits. With voice only, if you encode with 7 bits per level and you sample at 8,000 hertz, the reproduction at the receiver is generally considered good enough quality, a high quality for voice. In other applications, music and so on, well, you maybe need different number of levels.
This is the estimation or exactly.
No, and the sampling rate is exactly, the number of levels is an estimation.
In this audio format, it's not enough 44 kilobits. Then we have 96 sampling rate, and that's
The sampling theorem tells us if we ignore the number of levels, so if we had an infinite number of levels, if we sample at twice the highest frequency component, we can perfectly reproduce the data. If we sample it 3 times, there's no benefit in terms of accuracy. We'll have a larger file, but the accuracy will be no better. If we sample it less than twice, then we know that the accuracy will not be to the optimal value. That's what the sampling theorem tells us. So it gives us a guideline how often we should sample. Of course, the more often we sample, the larger the data. So often you'll see voice sampled at 8,000 hertz and at 7 bits per sample, giving us, what, 56 kilobits per second for a single voice communications. And that finishes us on PCM. There are some ways to improve it. It's the very basic scheme. There are improved schemes to take advantage of non-linear coding. You can look at that in your own time, I think. There's an alternative, delta modulation. There's some example of how it works there. But that's all I want to say about PCM, because we want to finish that last topic in the next 15 minutes. So that was coming back to our scenario here. Our amplifier sent our analog signal to my laptop. The analog signal, the audio, is input as an analog input as analog into my laptop, and it converts it to digital, for example using PCM. So my laptop has bits, and it can send those bits as a digital signal over Ethernet or as an analog signal across the wireless LAN using some of the techniques we've covered before. Coming back to my wireless transmitter. Originally analog data, the microphone sends it to the wireless transmitter. Frequencies ranging from, say, 0 up to 4 kilohertz, maybe some slightly higher ones from the noise in the background. This transmits at, I think it's around 670 megahertz. So it's not sending signals from 0 to 4,000 hertz, it's sending signals around 670 megahertz. It's sending analog data as an analog signal, but it's shifting the frequency at which it transmits. How does it do that? That's that last topic. What we do when we want to transmit analog data as an analog signal, often we want to create a signal that is appropriate to transmit across our medium. If I try and transmit a signal which is from 0 to 4,000 hertz from here to the wireless receiver, this is a very low frequency signal. We know with different frequencies they can propagate in different manners, over a different distance and through obstructions in different ways. Another thing that we haven't said, but generally, or not generally, always, the lower the frequency, the larger antenna that is needed. To transmit low frequency signals, you need a big antenna. So if I want to transmit 4,000 hertz signals, I need a very big antenna here. If I want to transmit 600 megahertz or 700 megahertz, my antenna can be much smaller. Small enough to fit in here. If I wanted to transmit 4,000 hertz, I'd need a much larger antenna, not convenient to use. So often we move the frequency at which we transmit our analog data. How do we move it? Well, the techniques we use is we either vary the amplitude, the frequency and phase of some carrier signal. So what we do is we have our input analog data, another carrier signal, and we modify the carrier signal, the amplitude, frequency or phase of that carrier signal based on the input analog data. That's one more mathematical illustration of it. This one shows just as well. This is an example of amplitude modulation. First, this is the input data, the input analog data or analog signal. All right, it's very simple. It's just a sine wave here. In a more complex case, it may be that signal I showed in my example of the recording, the voice going up and down. That's this middle one. This is our carrier signal. With amplitude modulation, what we do is we modify the amplitude of our carrier signal depending upon the amplitude of our input analog data. And we see this is the output. Take this carrier, when our input is high, make the amplitude of the carrier high. When the input is low, make the amplitude of the carrier low. And we get this output signal. This is the signal which we transmit with amplitude modulation. We can see the shape here following our input data. So let's consider the case with our voice using this wireless transmitter. The input analog data to my wireless transmitter is my voice. So containing frequencies of, let's say, 0 up to 4 kilohertz. In fact, there may be other signals coming from the air conditioner and so on, so it may be higher than 4 kilohertz. And that's the input analog data. We could plot it like the blue plot that we had in the example before. And with this wireless transmitter, it has a carrier signal. And the specifications of this device says that, in fact, there are a range of frequencies, but one of the frequencies is about 670 megahertz. So this wireless transmitter in my pocket transmits a signal with a center frequency of 670 megahertz, and it uses a bandwidth of 200 kilohertz. The bandwidth of my voice was 4 kilohertz, from 0 to 4 kilohertz. The bandwidth transmitted by the wireless transmitter is 200 kilohertz. So if we drew a plot of the spectrum of that signal, The bandwidth is 200 kilohertz. The center, let's say the center is 670 megahertz. So what does it do? It ranges from 669.9 to 670.1 megahertz. That is, if we start at 669.9 megahertz and go up to 670.1 megahertz, that's a width of 200 kilohertz, or 0.2 megahertz. 0.2 megahertz is our bandwidth of 200 kilohertz. So the plot of the spectrum would start from this 669.9 and go up to 670.1. That's the signal transmitted by the wireless transmitter. The shape of that signal, in fact, this wireless transmitter uses FM, frequency modulation. That's phase modulation and frequency modulation. The input analog data, my voice. The carrier signal, this is the frequency domain plot, that's the time domain plot. So it has a frequency, or center frequency of 670 megahertz. And the output from the wireless transmitter, what it does is it varies the carrier frequency. So although it's centered on 670 megahertz, it actually varies. When my input analog data is high, the frequency is reduced. We have a slower frequency here. And when it's low, the frequency is increased. So this would be the output signal produced by, or the output signal produced by the wireless transmitter would follow this principle. Of course, whenever my voice is high, if we're using this approach, then the frequency would be slowed down. Whenever my voice is low, it would be increased if we follow this approach. And that will be the signal that's transmitted. Transmitted, centered around 670 megahertz. The receiver receives that signal and it basically measures the frequency. If the frequency is low of the received signal, then there's a high amplitude of the output analog data. If the frequency is high, then there's a low amplitude of the output analog data. And the receiver reproduces the analog data here, and in our case sends it down to the amplifier. FM radio, that's how it works. AM, amplitude modulation, is AM radio, frequency modulation. AM, so here we vary the frequency of the carrier signal depending upon the amplitude of the input data. Phase modulation, vary the phase of the carrier signal. You see the phase, remember the phase is like the shift. Vary the phase depending upon the input amplitude. Amplitude modulation, vary the amplitude of the carrier signal depending upon the amplitude of the input signal. PM and FM are very similar, yes. We get the same results effectively.
Why FM is better voice, not better sound than AM?
Why is it better than AM?
FM is stereo, nice voice, more.
If you talk about radio, the radio channels have a larger bandwidth in the FM.
FM is on the megahertz and
yeah.
58 megahertz, and AM is 1,000,
Lower.
lower.
Yeah.
So bandwidth of FM is more bandwidth.
Yep. It's also to do with which one's better, the electronics to generate those signals. Which ones are easier to generate?
And in the waveform, is it easy to upgrade by noise by AM? Easier or not?
Noise, I think noise will have the same impact on both of these. That is, we still have to deal with noise. And other artifacts, other impairments need to be dealt with. So that covers our 4 different cases. This was the frequency modulation is used across our wireless link, sending analog data as an analog signal. And the other components of the analog signal, we don't necessarily have to do this modulation. We can send the signal as is. But in some cases, we'll do modulation to produce a signal with the appropriate characteristics. So in our scenario, we've seen all 4 cases. Any questions about any of those 4 cases?
Phase modulation or anything?
Phase modulation is used in some cases. Where? I don't know. I'll have to look up.
We're not PM radio, no.
No, but you see that phase modulation and frequency modulation are essentially the same. It's more to do with how it can be implemented. Any other questions? Quiz. There'll be a quiz next week. When do you think it should be? Wednesday or Thursday? Quiz on Thursday next week. Quiz Thursday, exam the following Monday. I think, from memory, the exam's on Monday.